Hello, my name is Dubiński and I have the pleasure to present to you towards more realistic membership inference attacks on large diffusion models. This is a joint work with my collaborators Antoni Kowalczuk, Stanisław Pawlak, Tomasz Trzciński and Paweł Morawiecki. Diffusion models such as Stable Diffusion, Midjourney or DALL-E are state-of-the-art image generators that have amazed the world with their capabilities. Such models are trained on billions of image and text pairs. However, large data sets scrapped from the internet often violate copyrights of individuals, such as photographers or artists. In this context, it is crucial to be able to confidently answer if a given data sample was used to train a particular model. This problem is known as membership inference. We select a data sample S, we query the machine learning model M with the sample, and by analyzing the model behavior, we try to determine if the sample S was in the model's training set, so-called members, or not, so-called non-members. Membership inference leverages the observation that machine learning models minimize their loss on the training members set. If a loss of a given sample is lower than the threshold, then this sample is labeled as member. Otherwise, it's labeled as non-member. In our work, we demonstrate the limited effectiveness of existing membership inference attacks against large diffusion models. We highlight the common pitfalls in designing the evaluation setup, and we propose our own data set for evaluating membership inference attacks on large diffusion models. Diffusion models are trained by iteratively applying noise to the input data and training a neural network to iteratively reverse this process by predicting the noise added at each step. In our work, we focus on Stable Diffusion, which is a state-of-the-art latent diffusion model which runs the diffusion process in the latent space of a powerful autoencoder. This model is equipped with a text encoder to condition the generation process using text prompts. In our work, we target Stable Diffusion 1.4. However, to evaluate the effectiveness of membership inference attacks, we need members and non-member samples. The most straightforward approach would be to use training data as members and test data as non-members. However, there is no test set left for Stable Diffusion, as all available data was used for training. We could try to split the data into train and test set and train the model from scratch. However, the cost of training Stable Diffusion from scratch is very prohibitive. We could fine-tune the model another data set, which we could easily split into test and train set. However, fine-tuning makes membership inference attacks easier and unrealistic. So we decided to take a different approach. We use training data as members and we collect new data to use as non-members. However, we need to make sure that the new data is from the same distribution as the members' data. Stable Diffusion 1.4 was trained on a subset of Lion dataset, which is a massive dataset of images and captions scrapped from the internet. We use Lion as aesthetic version 2.5 dataset as a source of our members. This dataset was used to train this Stable Diffusion version. We use Lion to be multi-translated as a source of non-member candidates. This dataset contained images with captions that were machine translated into English. We do not modify the Stable Diffusion model in any way. We do not perform any fine-tuning. Instead, we gather non-member samples that have the same distribution as member sample used for training. First, we need to remove duplicates of member samples that also appear in the non-member set. We do this using L2 threshold between clip embeddings of the images. Then we sanitize the member set. We use binary classifiers for filtering member samples that are easily distinguishable from non-members based on their text or image embeddings. In this way, after the duplication and sanitization, we arrive at two sets, members and non-members, which are not distinguishable for each other based on their text or image embeddings. We treat those two sets as an evaluation data set, which we call LionMe. On this dataset, we execute new and known membership inference attacks. On an exemplary setup with model fine-tuned on limited number of data, which we called Pokemons, selected attacks achieve remarkable performance, even close to 100%. However, for our proposed rigorous LionMe setting, we observe a drastic performance drop. This shows that membership inference attack for large diffusion models in realistic scenario still remains an open challenge. In our work, we demonstrate the importance of proper setting in evaluating membership inference attacks for large diffusion model. We propose an approach that does not modify the original stable diffusion model and focuses on creating a fair dataset for evaluation, which we call LionMe, and make openly available. Thank you very much for your attention.